called the divergence test. Okay, and this is the most simple test. You take a look at the limit as n goes to infinity of your sequence. And if that does not approach zero, you most certainly know the series diverges. If we're not getting to the point where we're adding 0 and 0 over and over again, there's no way that that sum is going to approach some number. Okay, so that's the idea. Let's take a look at 4 special types of series. And you're just going to want to know these. You're not going to understand all the reasons today, but in time you'll understand why some of these do what they do. So hang in there, but you want to kind of know these 4. These are 4 that we often compare things to a lot as we move forward with this unit. So the first up are arithmetic series. You may remember those from Algebra 2. That's where we add the same amount from term to term. Well, those will be linear functions. Okay, if we're adding the same amount from term to term, for example, 3 plus 5 plus 7, ... Okay, that's an arithmetic series, right? The first term is 3. We're adding 2 each time. You may or may not recall the general rule for these things. It's the first term plus n minus 1 times the common difference, which here is 2. That's what we're adding each time. And if we clean this thing up, we get a linear function back. Okay, so arithmetic series will always be linear functions. So if we have a summation with a linear function in it, we know that that's going to be arithmetic. Well, linear functions go off to infinity, right? If we add these numbers together over and over and over again, that's going to go off to either positive infinity if the terms are positive, or if the slope is negative, it'll go off to negative infinity. So, moral of the story, if we have an arithmetic series, that thing will always diverge. Okay, let's take a look at a couple examples here. So I have the summation as n goes from 1 to infinity of 2n. Now 2n is linear, right? That's n to the first power, so that's kind of what we're looking at. This thing is going to diverge. And pretty easily we can tell if we start ripping out some terms here, 2 plus 4 plus 6 plus 8. Yeah, those things are getting bigger and bigger. Looking at the limit as n goes to infinity of the sequence, 2n, well, that's going to go off to infinity. Therefore, this series diverges. Looking at the next example, we have the linear function negative n, right? That's comparable to y equals negative x. All right, if I plug the values in here, it's just going to get larger and larger in the negative direction. Here, the limit approaches negative infinity and once again diverges. Okay, so, if we have a bunch of problems in front of us and we see that we have a linear function, we know right away. This is an arithmetic series. This thing's going to diverge. We really don't have to do too much more work. Okay, what we should show is that the limit does not equal 0. Okay, look, the limit approached infinity does not equal 0. Did not equal 0. Okay, the next up are geometric series. Again, something you studied back in Algebra 2. That's where we're multiplying by the same amount from term to term. These show up in the form of exponential functions, right, because it's repeated multiplication. In terms of their summations, they come in a couple of different forms. They're basically the same. In some cases, you may have an r to the n minus 1 as the exponent. Starting at n equals 1. If you plug 1 in, you notice the first r you get is r to the 0. Sometimes the indexing begins at 0, and it could be written as r to the n. Again, if you plug 0 in, you notice that you get r to the 0 back first. And in either case, plugging in the first value of n, we get back a. Okay, so a basically represents the first term of our geometric series. Plug in the first value of n to get that number, okay? And r is what we call the common ratio. Well, for these to converge, the common ratio needs to be less than, the absolute value of the common ratio needs to be less than 1, which is to say that r itself is some number between -1 and 1, okay? And think about that for a minute. If you have a fraction between -1 and 1, what's going to happen if you keep multiplying that fraction by itself over and over and over again? So like -1/3, if I multiply that over and over again, we get what? 1/9, -1/27, 1/81, right? So on and so forth. Those things certainly approach 0 pretty quickly. If you have a number bigger than 1 that you're multiplying over and over again, right? That's going to get big quickly. It certainly isn't going to approach 0. All right, so if we have a fraction that's between -1 and 1 as our multiplier, as our r value, these will converge. If r is not between -1 or 1, this thing will diverge, okay? And try to make sense of the algebra here. If the absolute value of r is less than 1, that really means r itself is going to be some number between -1 and 1. So again, if I take like, -1/3, right? The absolute value of that is 1/3, comes back less than 1. Okay. Okay, so as a reminder for the sum formula for geometric series, the sum of the first n terms is a times the quantity 1 minus r to the n over 1 minus r. Now, remember, r, if we're going to assume this, if this is going to converge and this is going to have some sum, this is actually one of the few series that we'll be able to actually find the sum of convergence for. Most of the time, we won't even know what things add up to. We'll just know whether or not they're going to converge or diverge. But in this case, let's assume that we have a convergent geometric series. Under that assumption, we're saying that absolute value of r is less than 1, and as n is going to go to infinity. So think about what's going on with this right here. Right, if I have, again, we kind of talked about it a moment ago, when r was -1/3 and I kept multiplying it by itself over and over again, those fractions approach 0, okay? So that pink portion that I just highlighted, as n approaches infinity, is going to approach 0, and so what that allows us to do is really simplify the sum formula. Right? 1 minus 0 in the parentheses is just 1, and 1 times a in the numerator, just a. So we get this nice little formula back for the sum of a convergent geometric series. The sum of the first n terms is simply a over 1 minus r, where again, a is the first term of the series. Always plug in that first indexing value of n to get that number. It's not always just the number that looks like it's in front of r to the power. Okay, so a is the first term of the series, and r, again, is your common ratio. So let's take a look at a couple examples of these and see what's going on here. Okay, so here I have the summation as n goes from 1 to infinity of 3 times 1/2 to the n minus 1. So what we notice is that we have something that's an exponential form. That's how we know this is a geometric series. So looking at the thing in the parentheses that's raised to the exponent, we have an r value of 1/2. Well, since r is between -1 and 1, this thing's going to converge. Right? So we have a convergent geometric series, and we can actually find the sum. So a is going to be whatever I get back when I plug the first value of n in. Well, that ends up being 3 here. So we're going to have 3 over 1 minus 1/2, which is 3 over 1/2, which is 6. Okay, so if we were to rip out a bunch of terms here, the sum of these terms will get closer and closer to 6 the further out we went. Okay. In the next example, excuse me, we have 4 times 2 to the n minus 1 power. Again, that's in exponential form, so we know that's geometric. But if you look at the number in the parentheses, we have an r value of 2 here. Well, since r is greater than 1, this series diverges. And no sense in trying to find the sum because it won't have one. All right. Okay, next up is a very special type of series called the harmonic series. And we saw this in the example above. I just didn't call it that up there. This is the summation as n goes from 1 to infinity of 1 over n. Okay, specific n to the negative first power. Looking at the first 4 terms, 1 plus 1/2 plus 1/3 plus 1/4, and then it goes on forever. Actually diverges. Even though the terms themselves approach 0, okay, this thing diverges, and we'll have a better understanding of why in another lesson. Okay, but for now, your job is to just be on the lookout for this specific type of series. Okay, quick example: if we have the summation from 1 to infinity of 3 over n, that's really just a multiple of the harmonic. You are allowed to bring coefficients out front, much like with integrals. Okay, and what we have here is 3 times a divergent series. Well, 3 times infinity is still going to be infinity. Okay, so any multiple of a harmonic series is going to diverge. All right, so again, your job, recognize when we have a harmonic, 1 over n, any multiple of that, going to diverge. And last up for today are what we call p-series. That's the summation as n goes from 1 to infinity of 1 over n to the p power. These will converge if p is greater than 1 and will diverge if p is less than or equal to 1. Again, you don't really understand why today. We'll learn soon enough. I'll be able to show you why. But for now, just take my word for it. Okay, so looking at an example here, we have summation as n goes from 1 to infinity of 4 over n cubed. Again, you don't have to do this, but if you want, you can bring the coefficient out front. Okay, but now this matches the p-series. We have a p-series with p equal to 3, and that is greater than 1. Therefore, this will converge. Again, we don't know what it converges to, but it will converge. Okay, so let's try to take a look at a few examples here. We're going to identify the type of series. We'll determine if it converges or diverges. And if it's a geometric that converges, we'll find the sum. Okay, so first example here, summation. We have 3 halves, 1/4 to the n. Okay, and what do we have, folks? That's a geometric. Okay, we have a geometric. R is 1/4. Since the absolute value of R is less than 1, this is going to converge. Let's take a look at the sum. And again, look, I might go a lot faster than you. Pause as needed to try to practice problems, okay? Pause and then play when you're ready to keep on moving, okay? For my A value, if I plug 1 in, because we're starting at 1 here, notice, we're going to get 3/8 back. So we have 3/8 over 1 minus 1/4. And we are looking at 3/8 times 4/3. We got a half. Okay, so that'll approach 1/2. All right, next up. Okay, 4 minus n. Now, doesn't look exponential, but I notice n is to the first power. Oh, this is linear. We have a linear function. That means this is arithmetic. And so this will most certainly diverge. Okay, next up, certainly not arithmetic, doesn't look exponential. I could rewrite it in this form, however. Okay, and we have a p-series. Now, what you want to do is you want to leave that n in the denominator for the p-series. You don't want to rewrite that as n to the negative 1/2, okay? This is the form of a p-series, n in the denominator raised to some power. And here p is 1/2, which is less than 1. And so this will diverge. Okay, greater than 1 converges, less than or equal to 1 diverges. Okay, next up. Yeah, this is exponential, and so is geometric. Okay, now the R value here is 3/2. Absolute value of R is greater than 1. Therefore, this will diverge. And next up, summation as n goes from 1 to infinity of pi e over the square root of 2 times n. Certainly not arithmetic, certainly not exponential. Oh, you know what? If I factor out the coefficient here, we have a multiple of the harmonic. And so this one diverges. All right, so that's it for this lesson. Give the worksheet a try, give the problems a try, see how you do with this stuff. This is just the tip of the iceberg. You're going to learn a lot about this stuff in the coming days. Do your best to keep up. Feel free to check out other videos online. And, when we get back together, we'll tie it all together again. All right, have a good day, guys.